Hi everybody, Mr. Garrett here, and we're going to go over a little bit of 6.1 and 6.2, which is talking about rational exponents. We're first going to talk about what they are and how we use them, and the second part is going to be using their properties to simplify and evaluate those rational exponents. So the first thing that we're going to go over is what a rational exponent means, and really when we start off talking about this, we need to understand that a to the 1 over n is equaling the nth root of a. And we talked about this a little bit in the last video. But I wanted to get more into this part right here where we're talking about a to the m over n. And that's equal to the nth root of a to the m or the nth root of a raised to the m. We can use it one of two ways. Usually it's going to be this way because doing the nth root of a will make it a smaller number, and we can do some of that without a calculator. And so that's going to help out a little bit. But hopefully we'll see how that works. The first thing here is going from exponent form to radical form. And you can see right here, 44 to the 1/6 power. That's like this one right here. And so we would just say the 6th root of 44. Now we don't know anything that raised to the 6th power is 44, so we're just going to leave it in that form. Same thing here, 9 to the 5/3 power. Well, we could write that as the cube root of 9 all raised to the 5th. Or we could write it as the cube root of 9 to the 5th. And here's an example of why we would usually write it this way, because the cube root of 9 would be a small number. It would be like less than 2, or no, less than 3. And then raising that to the 5th we could do. But here, doing 9 to the 5th first, that's a huge number. And so doing 9 to the 5th and then trying to take the cube root of that would make it a little bit more difficult. So either one of these is okay, but typically we're going to use this form first. If we're going from radical form to exponent form, we're going to do the same thing. 8 to the 1/4 power is the 4th root of 8, and that's because this bottom number, whatever goes here in the root, is the bottom number. Whatever goes here in the bottom part of the fraction goes where the root is. The top number, let me use a different color here, the top number goes as the exponent. And so the top number always goes as that exponent, and that's how that works. Let's write this other one out. Cube root of 6 squared, well, that would be 6 to the 2/3 power. And again, the number in top of the root there goes on the bottom. The exponent goes on top of the fraction. Okay, so hopefully that's pretty understandable and pretty easy to do. The next thing we're going to do is we're going to evaluate some of these. And so you can see right here, the way this is set up is I can do the cube root of 8 squared. Well, the cube root of 8 is easy. That's 2, and then 2 squared is 4. Now, had I done this in the other way, I would have said the cube root of 8 squared, which would have been the cube root of 64, which if I knew the cube root of 64 is 4, that's easy. But here, you can see like this here. The 4th root of 81 is 3. 3 cubed, 27. If I were to, again, split this up and say the 4th root of 81 cubed, well, if I cube 81, let me just get it in here real quick. 81 to the 3rd power, that's 531,441. And I'm pretty sure most of you don't have memorized that 531,441 and the 4th root of that is 27. But if you put it in on your calculator, you would get that. But we really, really want to try doing this way because we can do it without a calculator. Let's try these over here. 4 to the 5/2 is going to be the square root of 4 to the 5th power. Well, what's the square root of 4? 2. 2 to the 5th is 32. And that's easy. If I would have done it the other way around and said the square root of 4 to the 5th power, well, 4 to the 5th power is a really big number. 4 to the 5th is 1024. And then if I square root 1024, I get 32. But I can't do that without a calculator. This I can do with a calculator. Same thing down here. 27 to the 2/3 power means the cube root of 27, which we should all know, squared. Well, cube root of 27 is 3. 3 squared is 9. Now I have some visitors.
Are you taking a video?
So what we have there is the cube root of 27 squared, which is 3 squared, which is 9. That works out really well. Again, if I were to try and write it out the other way and say the cube root of 27 squared, well, the cube root of 27 squared is a really big number. 729. So the cube root 729. And if I were to write cube root of 729, you might know it's 9, but you're probably going to have to use your calculator. So usually when we write these out, we want to write it out as a root first, then raise to the exponent, and then go in from there. All right, so let's move on to some other ones. Now in 6.2 we talk about exponent properties, and the exponent properties are the same as we've done before, so I'm not going to go over them. The hardest part is we're dealing with fractions now, and fractions are everybody's favorite thing in the world. But if I had something along the lines of this, where I had to add two fractions together, when we add or subtract we need to get when we add or subtract fractions, we need to get common denominators. And so when we get common denominators, we're going to look to see what number 3 and 5 both go into evenly. 15 would be that lowest number, and so that's the lowest common denominator. And so to get that, I'm going to multiply this by 5 over 5, because 5 over 5 is 1. I'm going to multiply 2/5 by 3 over 3, because 3 times 5 is 15. When I do that, what I get is 5/15 plus 6/15. Now that I have common denominators, I add the numerators and I get 11/15. And that's my solution. Okay? So whenever we have to add fractions together, we're going to try and get common denominators. If I multiply fractions, say 2/3 times 1/4, all I need to do is multiply the tops by the tops and the bottoms by the bottoms. 2 times 1 is 2. 3 times 4 is 12. 2 over 12 reduces to 1/6. Now one little trick that I could use here is, as I have 2 over 3 times 1 over 4, notice how the 2 and the 4 are multiples of each other. I could cancel this 2 and make the 4 2, because 2 goes into 4 twice, and then that would make it 1/6 right away. Here I'm reducing, then multiplying. Here I'm multiplying, then reducing. Either way is perfectly fine. The other new thing that we have here is the radical properties, and the radical properties kind of follow the same idea as the exponent properties. So whenever we're multiplying underneath the radical, I can break it up into the radical of and multiply both those. Or if I'm dividing underneath the radical, I can break it up so it's a radical divided by a radical. Just so long as those radicals are the same. If this were a cube root of x and a 4th root of y, I cannot multiply those two together because these roots are different. If they are the same, then I can add or multiply them together. All right? Now, let's simplify a few things. Here we have 5 to the 1/4 times 3 to the 1/4. Again, those are both 1/4. So what I can do is I can say that's going to be 5 times 3 to the 1/4, and 5 times 3 to the 1/4 is 15 to the 1/4. Now I could write it in radical notation, which would be the 4th root of 15, but either one of these would be perfectly acceptable, and I cannot simplify them anymore because there are no perfect fourths that go into 15. Remember, our fourths are 1, 16, 81, 256, so on and so forth. So none of those go into 15. Here, what I can do is I can say the 4th root of 2 times 8, which would be the 4th root of 2 times 8, which is 16. Now this I can simplify because 2 to the 4th is 16, if I remember my perfect fourths right. 1, 16, 81, yep, 2 to the 4th is 16, and so that's 2, and that's my simplest form. Here I can again add these exponents, and I'm going to have 5/3 plus 4/3. Well, what's 5/3 plus 4/3? We have a common denominator. That means it's going to be x to the 9/3. 9/3 is just 3, and so now I get x cubed. This is what I really want to spend a little bit of time on, though, is the cube root of 16x to the 4th. When we break this up, we want to break it up as if we're working with just the numbers and just the x's. And so I'm going to say it's cube root of 16 times the cube root of x to the 4th. Now, we've done this before where we've simplified these with square roots, but with cube roots, instead of breaking it up into perfect squares, we want to break it up into perfect cubes. So I'm going to break it up so it's a perfect cube times a perfect cube, or a perfect cube times another number. Now, my perfect cubes go 1, 8, 27, 64, 125. Do any of these go into 16? Yeah, 8 does. And so 8 times 2 is 16. And what happens now is I'm multiplying the cube root of 8 times the cube root of 2. The cube root of 8 is simply 2. The cube root of 2 is just the cube root of 2. Same thing over here. I want to break this up into perfect cubes. And I'm going to say the cube root of blank times the cube root of blank. Now, if I were to break this up, I would want to make it so it's a multiple of 3 here. And in this case, it's the cube root of x cubed. Well, if x cubed is underneath the 1, x has to be underneath the other, because x cubed times x is x to the 4th. What that's going to give me is x times the cube root of x. Now, since this is all multiplication, what I'm going to do is I'm going to take the two things outside the radical, 2x, and I'm going to keep them outside the radical. And I'm going to take the two things inside the radical and put those together underneath the radical, and I'm going to have the cube root of 2x. So this is my final simplified answer, 2x times the cube root of 2x. And I'll probably have to do a couple more examples of these a little bit later, but we're going to move on and do one last thing. The last thing is about adding or subtracting. Now, when we add or subtract, it's very, very important that whatever root we're working with, we have the same root. And so you can see here, the cube root and the cube root, that's good. And then we got 5 and 5. So we're dealing with the cube root of 5. Now, this is really simple if you listen. If I have 6 cube roots of 5 and I add 2 cube roots of 5, I now have a total of 8 cube roots of 5. That's it. That's as much as I can do. I can't simplify the cube root of 5 anymore, and I can't do anything with that 8. If we look at this other problem, it says 5 square roots of 5 minus the square root of 45. Now, at first glance, I'm going to look at this and say, square root of 5, square root of 45 doesn't quite really work because the square roots don't have the same number underneath them. However, if I break up the square root of 45, I can break it up into 9 and 5. Square root of 9 is 3. Square root of 5 is the square root of 5. And if I have 5 radical 5s, or 5 square roots of 5, minus 3 square roots of 5, I now have 2 square roots of 5. And that's my final answer. So I know we've covered a lot. I want you to go ahead and take a look at some of the practice problems, maybe replay the video, look at the exponent properties, take a look at the book, see if that helps, and try out 6.2 worksheet. Thanks a lot. We'll talk to you soon.